morning, ladies and gentlemen. My name is Dr. John Belkowitz. Alright, so welcome back to Intelligent Concrete, where we make concrete do the impossible. Today we're talking about high-range water reducers because it's high-range water reducer flower week, brought to you by the dandelion. Not only is it a pretty flower, but it tastes good too. So let's get into this. I wanted to do a video on high-range water reducer chemistry, why there are so many different types out there, and to do that, I got to go through a bunch of stuff. So just recognize all this shtick that I'm going into right now is just fodder for the most important piece of this. Why do we care about the cementitious chemistry when it comes to high-range water reducers? Okay, so the first thing is, why do we use high-range water reducers? And there's 4 reasons. The first one is the strength of the concrete, which is totally dependent on our water cementitious ratio. So if we want the same fluidity out of our concrete, but we want it to be much, much stronger, we use a high-range water reducer to yank out that water to make the glue of our concrete less dilute, more concentrate, and drive up our strength. The second thing is durability. With that reduction in water is a reduction in permeability, or an increase in our density and a reduction in our pore connectivity. And normally those pores not only mean lower strength, but they also mean more aggressive materials can migrate into the concrete and cause wear and tear, whether that's chemical or physical attack. Third reason is increasing the fluid properties without causing segregation. In the past, before we had high-range water reducers, we had mid-ranges and normals, which we'll talk about here in a little bit. But to get a highly flowable concrete, either we had to use high dosages of that stuff, which made the mix really sensitive, or high dosages of those water reducers plus a lot of water. So if we accidentally added a little bit of water, the mix would blow up in our face. So we want that highly fluid concrete or grout or whatever, but we don't want the segregation. And while you still can't have that with high-range water reducers, you have a little bit more control over it, assuming that you're using your high-range water reducer correctly. And the last one is increasing fluid properties of your concrete to accommodate for a higher reinforcement density. Now, if you think about what a water reducer does to concrete and really the cement and water combination, you have to imagine, ding! You don't have to imagine. We have the picture. We drop our cement particles in our proverbial bucket of water. And there's all these ions on the surface of our cement particle and in our water too. And what ends up happening, because of that electronegative potential, the cement particles actually agglomerate around the water and trap the water. And that's what that next picture shows. Ding! That the chemical interaction between those cement particles, and if there's not enough water to push things apart or just to get in between those flocculates, it will trap that water, monopolizing that water that was intended not only for the fresh properties, but also for hydration too. What we want to use is these polycarboxylate comb polymers, which is a technology that was brought over from Japan, has been used here in the States since the early 2000s, and it operates off of steric repulsion. And so back in the day when we were using naphthalines and lignins, those chemicals alter the electronegative potential of that cementitious paste. So it's a change in the chemistry or the pH of that that's going to cause deflocculation. We're not using that here. We're using something called steric repulsion. And it comes from this comb, as it said, this polycarboxylate comb polymer. So it looks like a hairbrush comb, and here's a picture of one from Winterfield in 2007. Ding! But here's one, my graphical representation of it, where you have this backbone that has teeth on either side of it. One set of teeth on the back side of the backbone is for adsorption to the cement particle surface. And that's the focus point of this article, and we're going to get to that here in a second. The other piece of that, the teeth from the comb itself, they're going to interact with adjacent teeth from combs that are adsorbed onto adjacent particles. And what happens is these things, just like as the name implies, they push each other away through steric repulsion. So you have like charges at the end of these combs, and basically they push each other away, and that force, that pushing force, is radiated through that polycarboxylate to the cement particle, and that's what causes our deflocculation. So you're not getting that change in your electronegative potential of the pH of that cement paste to create that deflocculation. It's a mechanical approach. So the next picture, ding, shows a bunch of these different polycarboxylate comb polymers, and the PCP that is just it's more of a structural name of the component. It doesn't really talk about the chemistry of that polycarboxylate. Now, if we change that polycarboxylate comb polymer to a polycarboxylate ether, now we're talking more about the chemical makeup of our comb itself. And as you can see from this paper that was, again, Winterfield in 2007, there are so many different types of combs with different types of teeth. And remember, the teeth on the bottom side or the back side of the comb is to adsorb into the cement particle, and the other teeth is to push the adjacent polycarboxylate away. Ding! Here's another picture of it. Before we were looking at actual representations, rudimentary. Here's another rudimentary representation of one of those monomers that's going to be part of that polymer chain. So a polymer is a building up of different monomers, and that's what we're doing here. We're taking these monomers of a certain chemistry that interacts both with attaching itself to the cement particle and then also acts as a mechanical action to deflocculate those cement particle and water combinations. And ding, this is what it's doing. Now granted, this is a rudimentary, not to scale drawing, so the polycarboxylate comb polymers are not actually this big. They don't cover, one does not cover the entire cement particle. You're actually going to need a lot in a localized area to cause that deflocculation. But as you see, they're going to get in between each other. They're going to attach onto the cement particle surface, and those external teeth are going to push each other away to cause that deflocculation. And all of that is based on the cementitious chemistry. And what I mean by that is the adsorption of the polycarboxylate to that cement particle surface is so important. If you have the wrong teeth size and the wrong teeth density to match the cement chemistry, what ends up happening is instead of that steric repulsion or that energy from that steric repulsion being transferred from the polycarboxylate to the adsorbed surface to the cement particle, it might act like a fulcrum, where the energy, instead of being transferred in a rigid connection, it might actually float around. And you might get an absorption that's not a true adsorption, which will cause that, but you might need more of that polycarboxylate, a high-range water reducer, to get enough of those polycarboxylate chains on the surface to change that fulcrum energy into something that would be more akin to that rigid connection and that energy that is transferred to the cement particle for deflocculation. So the reason why we care about all of this, and just to finish this up, is we're using high-range water reducers to do two things. Create a more fluid concrete that's also a stronger and more durable concrete. And if we don't choose the right polycarboxylate or the right high-range water reducer for our cementitious package, you're going to be throwing your money away and not getting the properties that you want, which is workability, your setting time, your strength, and that durability. Now, how do you choose the right one? You don't. You send your cementitious material, especially if you're a ready mix provider, to your admixture supplier, and they figure that out for you. Now, if you have the education or if you've been around the block a few times in your experience that you know a certain cementitious package works with a certain high-range water reducer, go for it. But it never hurts to send a 3-pound bag of your different cementitious materials and let your admixture supplier figure that out for you. They'll get you a more exact high-range water reducer, not only for your cementitious package, but also for your needs. And if there are any problems or if there are any changes, they can help you find one that's newer and probably a little bit more accurate to the type of concrete that you're making. So hopefully you learned something today. Don't forget to like and subscribe. Ding that bell for notifications. Let us know your concrete concerns. Go concrete! Beat asphalt!